In a world ruled by gravity, one force dares to push back. A force powerful enough to lift ships and quiet enough to raise a single leaf on a pond. They call it buoyancy. 2,000 years ago, one man uncovered this secret, a principle that would change the fate of every floating object on the earth. When gravity pulls down, buoyancy pushes back. Two forces, one battle. A solid block of steel is doomed to fall, but shape it into a ship and the ocean bow into it. Because floating isn't about weight, it's about density. As pressure crushes the deep, one rule stays unbroken. Buoyant force does not change with depth, it's the same in the shallows. In oceans, in lakes, even in the sky, buoyancy decides who rises. Submarines control it to dive, balloons rely on it to soar. This video discovers the force that lifts world, balances ocean. Will it float or will it sink?
Hello everyone. Today we will discuss about the buoyancy, understanding why objects float, sink, or stay suspended. So first, what is buoyancy? It is an upward force exerted by a fluid. It makes objects float or feel lighter and is caused by displaced water. So buoyancy is the upward force that a fluid applies on an object placed in it. This force helps objects float or makes them feel lighter because the fluid pushes upward whenever it is displaced. So, to understand more, we have the Archimedes principle. So, it explains the source of buoyancy, wherein upward force is equal to the weight of displaced fluid, and it applies to both liquids and gases. So, Archimedes' principle states that an object immersed in a fluid experiences an upward force equal to the weight of the fluid it displaces. This explains how buoyancy works in water and even in air. So how buoyancy happens? Objects pushes water aside, displaced water has weight, and this weight becomes the upward force. So, when an object enters water, it pushes water aside. The water that gets displaced has weight, and that weight becomes the buoyant force pushing on the object. So, how do things float, sink, or suspend? So, if buoyant force is greater than the object's weight, it floats. If it is smaller, it sinks. And if both equals and if both forces are equal, the object stays suspended at a certain level. Now, the buoyant force formula is equals to F sub B equals to density of fluid times gravity times the volume displaced. And it determines how strong the upward force is. So for an example, a boat floats because it displaces enough water to create a buoyant force equal to its own weight. Even heavy ships stay afloat by pushing a large amount of water downward. Boats are designed with wide and hollow shapes to displace more water. The more water displaced, the stronger the buoyant force pushing upward, preventing the boat from sinking. So to remember easily, Water pushes up exactly as much as it gets pushed away. That single idea explains buoyancy and Archimedes' principle.
Hey everyone, and welcome to the Buoyancy Trivia Sink or Swim. Have you ever wondered why some things float and others sink? Today, we're testing your knowledge with 5 multiple choice questions or trivias about buoyancy. Let's dive in. Question 1. The scientific principle that explains why massive ships can float is named after which ancient Greek thinker? A. Aristotle, B. Archimedes, or C. Pythagoras? The correct answer is B. Archimedes. That's Archimedes' principle. It states that the upward buoyant force of an object is equal to the weight of the fluid that object displaces. Question 2. Why is it significantly easier to float in the Dead Sea than in a regular swimming pool? A. The water is warmer. B. It has a high salt content. Or C. The magical mud. That's right, it's B. It has a high salt content. All that dissolves salt makes the water much denser. Denser fluid means a stronger buoyant force, pushing you up, so you float like a cork. Question 3. How does a submarine primarily control its buoyancy to dive underwater and surface again? A. Using its propeller. B. Extending and retracting fins. Or C. Filling and emptying ballast tanks. The answer is C. Ballast tanks. To dive, they flood these tanks with seawater to increase their density. To surface, they pump the water out with compressed air, decreasing their density. And that's it. How many correct answers did you get? Let us know your score in the comments below. Thanks for playing this episode of Buoyancy Trivia. Bye-bye!
Now let us solve this sample problem. For this problem, we are asked to find the vertical force needed to hold a piece of wood in place while it's fully submerged in water. The wood is about 305 millimeters square, which is 0.305 in meters, and it is 3 meters long. Its weight density is 6,288.46 newtons per cubic meter, and the water has a weight density of 9,810 newtons per cubic meter. Now let us solve for the volume of the wood. So the volume is equal to the cross-sectional area squared multiplied by its length. That would be volume of wood equals to 0.305 meters squared times 3 meters, giving us 0.279075 cubic meters. Now we solve the weight of the wood. So in this, we use the formula weight is equals to gamma of wood times its volume. So that is 6,288.46 newtons per cubic meter times 0.279075 cubic meters. That equals to 1,754.95 newtons acting downward. Now let us solve for the buoyant force. By Archimedes' principle, the buoyant force is the weight of displaced water. So we use the buoyant force is equals to gamma of water times the volume displaced. Since the wood is fully submerged, the displaced volume is the same volume we already calculated. So we compute 9,810 newtons per cubic meter times 0.279075 cubic meters. That would give us the buoyant force of 2,737.73 newtons acting upward. Now we apply the equilibrium of vertical forces. We take upward forces as positive. The forces acting are the buoyant force, upward, the weight of the wood, downward, and the applied force, F, also downward. For equilibrium, the sum of vertical forces is 0. So we write buoyant force minus weight minus F equals 0. Then we have to rearrange for F. And that would give us the final equation of F equals the buoyant force minus its weight. Then we substitute the values. That would be 2,737.73 newtons minus 1,754.95 newtons equals to 982.78 newtons. So the force required to hold the wood in position is approximately 983 newtons directed downward.
Hi everyone, so in this video, we're going to calculate the buoyant force acting on a fully submerged rock in water, and we're going to determine whether it will fall or sink. So we have here the given information, which is the rock has a mass of 32 kilogram and a density of 2,800 kilogram cubic meter. So our goal here is to find the buoyant force acting on the rock. So we have here then the water's density of 1000 kilogram per cubic meter. So the buoyant force is equal to the weight of the fluid displaced with the object. So volume of the rock is equal to the volume of water. So now we have then to find the density. So density is equals to the mass over volume. So in finding the volume, we need to have this equation. V is equals to mass over density, which has 32 kilogram over 2,800 kilogram per cubic meter. So we need to cancel those same unit, and results to 0.011 cubic meter. So the volume of the water is 0.011 cubic meter. And then we're going to find the buoyancy, or so it is density multiplied by gravity and volume. So density of the water is 1000 kilogram per cubic meter multiplied by the gravity, which is 9.8 meter per second squared, and the volume, which is 0.011 cubic meter. Then we're going to cancel those units that are the same, and then it will be given as 107.8 Newton.
Alright, so for the another sample problem, we have a standard basketball with a mass of 624 grams and a diameter of 24.3 centimeters. The question asks us to find the buoyant force on the ball when it is held fully underwater, and then decide whether it will sink or float when we let it go. So first, we need to calculate the weight of the ball, but we need to convert first the value of 624 grams into 0.624 kilograms. So from the previous lectures, we already know that the weight can be obtained by multiplying mass and gravity. So 0.624 kilograms times 9.8, which is the gravity, is equals to 6.121 newtons. So next, because the ball is completely submerged, It displaces a volume of water equal to its own. It's a sphere, so we will use the formula 4 over 3 times pi times r cubed. The radius is half the diameter, which is 0.1215 meters, and plugging that in gives us the volume of 0.00751 cubic meters. Now, to find the buoyant force, we will use the Archimedes principle. Buoyant force equals the density of the fluid times the displaced volume times gravity. So we'll multiply water's density, which is 1000, by the volume, and then by 9.81, which is the gravity. We'll get the buoyant force of about 76.93 Newton. So the ball's weight is about 6 newtons down, and the buoyant force is about 77 newtons up. Since the upward buoyant force is much stronger, the ball definitely floats when released. Finally, we want to know how much the ball sticks out of the water, but to do that, we will find the density of the ball. So the formula for the density is mass over volume. That gives us 0.624 kilograms times 0.00751 cubic meter, which is the volume. And that gives us the value of 83 kilogram per cubic over cubic meter. So that means 8.3% of the volume of the bulb is below the water, and 91.7% is above the surface. So I hope you understand our topic. Thank you for listening, and I hope you enjoy this video.